Um, so we were looking at the solution to equation which has got one derivative in it, and we had something like tau dqo dt plus qo is something like that. So that was our equation, and okay, so that was our equation, and what we said was that the qo is the variable that we are trying to get a solution for, and this guy here could be a constant, could be a function of time, but it is something that is given to us. So we said that in the class before that, we said that we could say that the right-hand side can be pushed equal to 0. You got the homogeneous solution, and then you got a particular solution for this by putting the right-hand side, and by whatever may be the means, you have got one solution. That's the particular solution. And the total solution is going to be the so-called complementary function, which is the solution to the homogeneous equation and the particular solution. For first order equations, a slightly better methodology exists where you have what is called an integrating factor, and the integrating factor is integral of e to the power of integral of whatever is there here. In this particular case, we said this is 1 by tau. So you just have 1 by tau dt, and if you take this guy and multiply this equation, then it becomes a total differential and you can easily integrate it. Okay, so that was the concept of the integrating factor. And then we looked at an example, and we used the integrating factor, and we got a solution. The integrating factor, a couple of comments on the integrating factor. When you are integrating this guy, we don't put the constant of integration. Even if you put it, it's fine because it's going to cancel on both sides. And the integrating factor type of a solution is going to give you the complete solution. There's nothing like a complementary function and a particular integral. So it's going to give you the total solution. Then we said that, okay, we make life a little bit more complex, and we said that the right-hand side has got some kind of a discontinuity, and if the right-hand side has got a discontinuity, so in this particular case, the discontinuity looked something like this. So there was some number was there. So the right-hand side was 1 from, let us say, 0 to some 1 unit of time, and then it was suddenly pushed to 0, and then the solution was required. So you went ahead and got a solution, but if you are going to use whatever mechanism we have seen so far, then you need to split this into 2. So you say that this, let us say, is time. This goes from 0 to 1, and 0 to 1, I have got this as the input, and from 1 onwards, I'm going to keep this as the input. But remember that when we do such a situation, we need to make sure that the variable that you are solving for is going to be continuous, okay, which means that I have this solution, and that whatever you got is the solution that we have, and then the solution to the next part, which is going to be this, is going to have an initial condition which is going to come from the solution from the previous part. Okay. So this was what we did as far as the discontinuity on the right hand side is concerned. And then we said that Okay, so somebody said that, okay, why are you saying that I'm going to match this y? Remember that y is the variable that you're trying to solve, and that has to be that has to be continuous. Okay, so if let us say uh, um, if I've got a temperature sensor, for example. Okay, so usually the temperature sensor you can model it in many different ways. So one of the ways in which you model a temperature sensor is this. It's not important if you don't recognize these terms, that's not important. What I'm trying to say is that this is the variable that is unknown, and this is the input, and this awfully looks close to this, right? So if I just take this MC downstairs here, this is H by MC, this is 1 by tau of this and this. So if this is a temperature sensor, and let us say I've got two tubs, and initially this guy is sitting outside, and let us say this is 100 degrees Celsius. I just take this and suddenly dip it inside, which means that the input to the system is 100. The sensor is trying to sense this 100, and so it is slowly going to want to move up. Say this is 100. Okay, this is exactly this situation. And then let us say this guy is 50 degrees. I remove this guy and plug that in here. So up to this time, whether it reached this or not is not important, and then it's going to go. So this guy here, which is the temperature of the sensor, is continuous, right? So the variable which I'm trying to solve is continuous, okay? So this, if you don't understand, that's perfectly fine. This is just to make sure that there is a physical example which is going to tell you that this variable is going to be continuous. Whether the slope is continuous or not is something that we don't know. In this particular temperature example, this fellow went like this and then it went like that. You can see that the slope is not continuous. But this is only one of the examples. So what we are saying is that the variable y is going to be continuous. Okay, so in this type of an approach. Then what we said was, okay, this is quite okay for me to do, but if I've got multiple steps, then it starts to become a little painful. So while you can do that, I'm not saying you can't, but is there something maybe better? Now, not necessarily easier, but another methodology which is going to be able to permit me to go ahead and get a solution. Okay, so we then said, okay, there is another powerful way of solution to these types of equations, and those are the Laplace transform methods that we started looking at. And the Laplace transform of a variable we said was integral 0 to infinity e to the minus st dt times that function. Okay. Integration we are all very comfortable with, so you can go ahead and integrate and then get whatever is going to be the transform. Only thing is that you are transforming from the time domain or the t domain to the s domain. Okay. That's all great as far as you can go back from the s domain to the t domain, because we live in the t domain and not in the s domain. My interest is in the t domain. Okay, fine. So the Laplace transform of the function t, we took another example, and then we did the algebra, and you found that the Laplace transform is going to be coming as now not a function of t, but a function of s. Okay. So far, this is all abstract. How it is going to help us, it's not clear. But nevertheless, let us just say that that was what was done. Okay. All right. Then we started looking at what is called the Heaviside step function. Okay, so what we say is that if I've got a function, right, and we are going to use the Heaviside function in trying to make life easier for ourselves. So we define the so-called Heaviside function as somebody who is going to have a value of 0 for t less than equal to 0 and t greater than 0, it is going to be unity. Okay, so this is the definition of the Heaviside function. Okay, so if I'm going to plot this Heaviside function, it's going to be 0 up here and then it's going to take a value of 1. Fairly straightforward stuff. Okay, so many times we are not interested in the function like so. So what we say is I'm going to also look at a Heaviside function where this t0 starts from there and then the Heaviside function takes off at time t equal to tau. Okay. I'm a little bit loose when I say time because this need not be time, it can be any variable. So it's just a variable t, it's starting from let us say whatever number. So at the t equal to tau, if I want that function to take off, then this is going to be what I have. So t minus whatever is there within the brackets, I make it equal to 0, I make it equal to 0. So for t less than tau, this fellow is 0 and for t greater than tau, this is equal to unity. Okay, so that's the definition of my Heaviside function. Okay. Alright, that's just a definition. Anybody have any trouble with that? The definition of the Heaviside function. We are going to use it. Alright. So then what we say is we also like to use something called the Dirac delta function. And what is going to be the derivative of the Heaviside function at this point? What is the derivative? How do I compute the derivative of a function? How do I get the derivative of a function? I take the function at a particular point which is downstream, which is let us say t plus epsilon minus h, let us say t minus epsilon, and then I divide it by 2 epsilon and take the limit as epsilon tends to 0. So that's how I would get the derivative in general of a function. So that's how I usually get the derivative of a function, which is to take the function and then get something on this side and get something on this side, subtract these two and then divide it by whatever is the interval and then take the interval to 0. That's the definition. So if I'm going to get the derivative of this function at let us say t equal to t0, so then I have got okay, so at t plus epsilon, which is now, so I've got a function which is looking like that, and now I have got, okay, so I have a function that possibly is going to be the derivative of this function between the plus epsilon and the minus epsilon. Okay. So suppose now I say that I have something like this. As of now, let us not worry about the Heaviside function. I just have a rectangle or a square or whatever it is, and this guy is equal to tau. This is tau minus epsilon and this is tau plus epsilon. Okay. And this is, let us say, t. So at t equal to tau, there is some number. At t plus epsilon, t minus epsilon, I have made this as some kind of a square, and I say that this guy is 1 by 2 epsilon. Okay. So the so-called area under this curve is equal to unity, right? Because the height is 1 by 2 epsilon, the width is 2 epsilon, 1 by 2 epsilon times 2 epsilon is equal to 1. Okay. So you define something called a unit step function. So this is a function that has got an area of unity. So this is called a unit impulse function or a unit step function, and this guy is going to be existing only in tau minus epsilon to tau plus epsilon. Okay, at this limit it exists, nowhere else it is existing. So this is 0 here and this is 0 here. So that's my unit impulse function. At the moment everything is abstract, but that's perfectly fine. So I've got a impulse function so-called, and I'm trying to say that I'm going to define this so-called delta, which is the unit impulse function, as saying that now I have got, let us say there is one Heaviside function like that, and I'll just draw something on top here. This is the other Heaviside function. So one Heaviside function starts from here, moves all the way down. Another Heaviside function starts here and moves all the way down. So what is this Heaviside function? H of t minus what? What is a Heaviside function that starts at tau minus epsilon and moves all the way down? This is 1. This is 0. What would I put in the brackets? Okay, what was my Heaviside function definition? H of t is equal to 0 up to t equal to 0. Whatever is inside the bracket, I'm going to make equal to 0. Okay, so t equal to 0, so this is my Heaviside function. So this is h of t. Okay. Now if I say that I have got my Heaviside function, which is at tau, this is 0, h t minus tau is equal to 0 for t less than tau, and t greater than tau, it is equal to 1. So this is the Heaviside function for that. Okay. Okay. So now what would be my, where did my definition? Okay. All right. So I have got my, this is what I'm trying to model here. Okay. So there is a Heaviside function, and I want a Heaviside function that is unity downstream of tau minus epsilon. So what should I have inside the brackets? T, right? If t equal to 0, it starts at 0. Right? If t equal to tau minus epsilon, it will start at tau minus epsilon, right? So what should I put here? T minus epsilon, tau minus epsilon. Okay. So I'm starting from tau minus epsilon. I'm not starting from epsilon, right? So it's like here. If this guy, now this guy is tau minus epsilon. This guy is tau minus epsilon. So at tau minus epsilon, which means that this is, right? Okay. So what should be my next, in the second term? T minus tau minus epsilon. Okay. Now let's get rid of all this stuff. Okay, so my Heaviside function starts at tau minus epsilon and stays 1 throughout. Okay, so that is h t minus tau minus epsilon. Okay, minus of a Heaviside function that starts from here. What would be that? t minus tau plus epsilon. Okay, so this would be minus h t minus tau plus epsilon. Okay, and now I just want the derivative, so I'll just divide by twice epsilon. Okay, so if I have got h t minus tau minus epsilon minus h t minus tau plus epsilon, I'm going to have just this here. Right? Only this part of that function is going to be there, and rest all is not going to be there. Okay. Now suppose I say that, now that's what's going to get me the derivative, right? So if now I make the epsilon tend to 0, if my epsilon tends to 0, then what happens to this guy here? This guy just keeps on blowing up, because now I'm saying that the height of this is 1 by twice epsilon, right? I've forced this area to become equal to unity, right? So this guy keeps on blowing up. So I don't know what that is, right? It is something. So I'll just say that it is delta, and I will call this a Dirac delta function. So essentially, the Dirac delta function is an impulse, a unit impulse function, but its magnitude is very large. I don't know what the magnitude is, but it is very large is what I'm saying. So a unit impulse function. So this is my unit impulse function. That's the way I'm defining the unit impulse function. And I'm saying that this delta is going to tend to the so-called Dirac delta function. Is that okay? We're going to use this now over and over again. Okay, once again for the last time, the unit impulse function is some kind of delta times delta t, and the delta times delta t is equal to unity, right? And as that delta t tends to 0, this delta is going to be called the Dirac delta function. Okay? Okay, these are just definitions that we are pulling along. So I've got now a Heaviside function which is giving me a step, and then I've got a Dirac delta function which is some kind of a derivative of this Heaviside function. Okay. Now in all of this, what we need to just remember is that if I'm going to have a unit impulse function and the unit impulse function delta t is going to go towards 0, then the magnitude is going to go towards a very large number. That's all it is. What that large number is something that we are not going to be too concerned about. All right. So now let us go ahead and see formally what is this integral of. Remember we said that the delta function is a derivative of the Heaviside function, which means that the integral of the delta function has to be the Heaviside function itself, right? So integral of delta dt is going to be equal to the Heaviside function, and this is minus infinity to infinity, which happens to be equal to unity. Okay, so the derivative of the Heaviside function is the delta function, the Dirac delta, and the integral of the Dirac delta is equal to unity, and it happens to have some kind of a meaning that we have attached to it, which is that delta times delta t is equal to unity. Okay? All right. Now, what happens if, let us say that we multiply this by some function f of t and try to perform the integration? I have a delta function. Now that we know what the Dirac delta function is, we say that the Dirac delta function delta t. What would be delta t minus tau? What would be delta t minus tau? Delta t is a function that goes to a very large number at t equal to 0. H of t is a function that is 0 up till t equal to 0. Whatever is there in the brackets has to be equal to 0. Okay. So if this guy is 0, right? So, and if I have some kind of a t scale, where is this guy going to blow up? This delta function? T equal to 0. So at t equal to 0, it's going to go to a very large number. What that large number is, I'm not concerned about as of now. Okay. Okay. What is delta t minus tau? Where will this guy blow up? Whatever is there within the brackets has to go to 0, right? Which means where will it blow up? T equal to tau. Okay. All right. Good. So at t equal to tau, this guy is going to be there. And what about the function at the rest of the t's? 0, right? So delta t is 0, 0, 0. Suddenly something happens and then 0, 0, 0. Delta t minus tau, 0 all the way up to tau. Suddenly something at tau, something happens and then again 0. Okay, now having understood that, what would this be equal to? What is the delta function? At 0, there is a large number, correct? So, which means that this guy is 0 everywhere except at t equal to 0. So, which means that only F0 will survive. Nobody else is going to survive, right? So, this guy, I'm just going to write it as F of 0. Okay. Only at t equal to 0, this fellow is going to survive. At all other locations, it is not going to survive. And delta dt is equal to 1. I understand delta dt integral equal to 1. Delta I don't understand, but that's perfectly fine. But I should understand what is delta dt integral. In an integral sense, the delta makes sense to me, right? The delta on its own may or may not make sense to me, okay? Alright, so now suppose I say delta t minus tau dt ft. What is that going to be equal to? What is that going to be equal to? It's f tau, right? Because this guy here is existing only here, and this is whatever could be f of t. So everywhere else you are multiplying with 0, everywhere else you are multiplying 0, except this location where it exists as f of tau, right? And then I know integral delta dt is equal to 1, and therefore this guy is going to be equal to f tau. Okay? This is all we need to understand as far as the Heaviside and the delta functions is. Okay. Once again, for the last time, the Heaviside function is a function. If I am going to say Heaviside open bracket t, whatever is there in the bracket, I am going to put it equal to 0 and say that the function is going to be 0 up to whatever in the brackets is equal to 0, and then it is going to be equal to 1 downstream. Okay, so that's my Heaviside function. Similarly, the delta function, whatever is there within the brackets, I'm going to equate it to 0, which means delta, if I'm saying delta t, then this guy blows up at 0. Integral of delta dt is going to be equal to 1. Okay. This much, if it is clear, I think we are in good shape. Anybody still have any trouble with that? Okay, great. Now we are going to use this. Our intention, once again, I would just put a disclaimer saying that the math guys are going to spend a lot more time on the delta and Heaviside functions. As an engineer, if we understand these properties, I think that's good enough for us. Okay? All right. So our interest, remember, all of this business started why? Why did we start all this nuisance? Because what we said was, we had an equation, there was a right-hand side, there was a discontinuity, and then we said that it was becoming a little painful to solve that. Is there another methodology that exists for us? Okay, so that's the basic reason. So we would like to use all of this in differential equations. Okay, so the use of the Laplace transform in the differential equation is what our main objective was. Okay. So let's come back to the main objective. This was some kind of an aside where we said that we need some definitions so that we can go ahead and work out some solutions to situations which are of interest to us. Okay, so we have a Laplace transform. Definition of the Laplace transform we said was 0 to infinity e to the minus st dt. That's the definition of my Laplace transform. Okay. All right. Now I have got an equation that perhaps looks like this. I would like to take the Laplace transform of this equation, which means that I need to know what the Laplace transform of a derivative is, right? Okay, so let's see what the Laplace transform of the derivative looks like. Okay. So I have Laplace df dt. Okay. So I make this df dt. How do I integrate this? Can I integrate this first of all? Integrate by parts. Okay. So this is a very nice tool that the mathematicians have given us, which is integration by parts. It works all the time. Okay. So let's integrate this guy by parts. Okay. So this is the first function times the integral of the second. This is a derivative, so this is f, right? So this is 0 to infinity, that's the first term, minus integral of the second, which is f, times differential of the first. So that's my integration by parts. Okay, okay. What is this guy here? What is e to the minus st f 0 to infinity? What is that? What is e to the minus s? Is this equal to e to the minus st f at infinity minus e to the minus st f at 0? Is that right or not? Yeah? Okay. So what is e to the minus st f at infinity? 0, right? Because I have got 1 by e to the minus st, and that term is going to pull this to 0. So this guy is going to go to 0. And what about this guy here? That is also 0? F of 0, great. So this guy, this is f of 0. Okay, so that's the first term there. Okay, what about the second term here? Does that look familiar? What is that? What is e to the minus st ft times minus s? S I will take out common. So I take this minus s out. This is plus s. And what is this here inside? This is the Laplace transform of f, that's all, right? This is f e to the minus st. That was the definition of my Laplace transform. We said that L of f is integral 0 to infinity e to the minus st f dt. This is my definition. So all that we have is this guy and this guy are the same, right? So this guy becomes minus f0 now minus f0 plus s times the Laplace of f. Okay. So the Laplace transform of df dt is minus f0 plus s Laplace transform of f. Have we made things simpler? As of now, we don't know. Okay. Maybe, maybe not. Okay. So now we have got Laplace of df dt is equal to minus f0 plus s L of f. We'll just jump a little bit, although we have not still done this, but what about L of d square f dt square? The Laplace transform of the second derivative. Can I just extract it from what we have done? You can of course go ahead and use the definition integral d square. That can be done, e to the minus st. Okay. But based on what we have, we can always write this as Laplace of df dt prime, right? And what is Laplace of df dt? Let me call this G, if you will. This is d dt of df dt. What is this? L of df dt. Instead of f, now I have got something called a G. That's all there is, right? So what does this become? Minus of what? G0. Okay, plus S L of G, right? And I already have the L of G upstairs here, right? So this is minus G0 and G is df dt, so this is minus f prime of 0 plus S of L of G. What is L of G? Laplace of G is right here, minus f0 plus S Laplace of f, right? So let's now not worry about this guy here. We just say that L of f double prime or the Laplace transform is equal to minus f prime at t equal to 0 minus S f at 0 plus s square L f. Okay. Okay. So all of this we are doing brute force algebra. Now let's go back to the question at hand. Okay. We said that we started out by looking at this situation, which was y prime just y prime minus y equal to 1 for 0 less than t less than 1 and it is 0 for t greater than 0. Okay. This was the original situation that we had. Okay. And then we digressed. We said, okay, now we want a definition of Heaviside function, we want a definition of the Laplace transform, we did all that, and now it's time to come back to the original question at hand. Okay. So this was the differential equation that we were trying to solve. Okay. Okay. Now let's go ahead and say what's going to be the Laplace transform of this. What is the Laplace transform of y prime? What is Laplace y prime? We just did that 2 minutes ago. This was minus y0 plus Laplace y, correct? So I take the Laplace transform of this and I want to take the Laplace transform of this. How do I take the Laplace transform of that? What is it that is there on the right hand side? That's the function, right? Now, armed with this business of the definition of the Heaviside function, can I just write it as one function rather than two pieces? Which says 0 to t it is 1, 0 to 1 it is 1 and 1 to very large number it is 0. I want now to write this as something so that I can put on the right hand side. What would that be? Is it possible, number one? If it is, what is it? First of all, is it possible? Okay. Yes or no? I have this thing called the Heaviside function, right? So can I use the Heaviside function to represent this guy? What was my Heaviside function? Heaviside function is somebody who just takes off and then stays like that, right? What do I have here? I have somebody who took off and then it came down also. So if I have somebody like this, now the Heaviside function, if I multiply it by negative unity, for example, then it will go like this, right? What would be h of 0 plus minus h of 0? What would be this function? It would be 0, identically 0 everywhere, right? Okay, so now let us say that this is h of 0. What would be h of 1? H of 1 would start at 1, it would go up, and then it would keep on going, right? So Heaviside 0 is somebody who starts here and then keeps on going, and I have got Heaviside 1 which starts here and keeps on going. So if I want this, then what do I do? I have got Heaviside 0 minus Heaviside 1, which is like this. This minus this is equal to this. Is that right? Yes, correct. So the right hand side, I'm going to just write this as Heaviside 0 minus Heaviside 1. Okay. So Heaviside 0 is Heaviside t, because t I'm going to make it equal to 0. Heaviside 1 means it is t minus 1. Right? Whatever is there inside is equal to 0 under the brackets. If it is, I want to make it 0. So Heaviside 0 is this function here. Heaviside 1 is going to be this function here. Heaviside t equal to 1. Okay. So this guy minus this guy is equal to this guy. Anybody not clear on that? Okay, good. So my right hand side is also taken care of. So I've got now, I have y, now I'll just get rid of this and I will say that this is Heaviside of t minus Heaviside t minus 1. Okay? Okay, so does that generate a new headache for me? Yes, because I need to know now. We have already said Laplace transform of this is this. So I need to know what is the Laplace transform of h of t, right? Because we are taking the Laplace transform on the left hand side, we would like to take the Laplace transform on the right hand side also. So what is the Laplace transform of h of t? That's what we want. Okay, so we'll do slightly general, which is h of t minus a. Okay, so if a equal to 0, it is h of t or anything, because I need the Laplace transform of t minus 1 also. Okay, so I have Laplace of ht minus a. This, once again, when you want the Laplace transform, you just have to go back to the definition. Okay, e to the minus st h t minus a dt. This goes from 0 to infinity. Now, I want to write this as, I want to get rid of this guy now. How can I get rid of this guy? By changing the limits, right? This guy is starting from 0 to infinity, and this guy says that up to t equal to a, I am 0, and then I am 1, right? So I just say that this becomes a to infinity and e to the minus st dt. That's all it is, correct? And I have now gotten rid of this fellow inside here. Okay. So Laplace of ht minus a is e to the minus st dt a to infinity. And what is integral a to infinity? I need to have a change of variables now, right? Let us just say that tau, of course I use this tau very much, but nevertheless. So let me say tau is equal to t minus a. I just use a change of variable, that's all. Tau is t minus a. I've got a dt here. What is dt therefore? A is a constant. So what is d tau equal to dt, right? So d tau is dt. So I'll get rid of this and make it a tau. What is t? T is tau plus a. So I've got this as tau plus a. And what are the limits? At t equal to a, what is tau? 0. So this is 0. Infinity will stay infinity. Okay. So we have changed the variable into another thing called this. Okay. And now, what is e to the minus sa? It's a constant, right? A is a constant. So I can take it out of the integral sign and say that this is going to be equal to e to the power of minus sa e to the power of minus s tau d tau 0 to infinity, right? And what is e to the minus s tau d tau? What is e to the minus s tau d tau integral 0 to infinity? Minus 1 by s, right? So I've got 1 by s here, that's minus 1 by s, and then there's a negative, so that makes it a positive. So this becomes e to the power of, so e to the minus as upon s. Okay. So the Heaviside, the Laplace transform of ht minus a is e to the minus as by s, and therefore h of t is equal to what? H of t is equal to Laplace of h of t is equal to what? 1 by s. Okay, 1 by s. All right. So now Laplace of y prime is minus y0 plus Laplace of y minus Laplace of y is equal to ht 1 by s minus ht minus 1 e to the minus as by s. Okay. I've just taken Laplace transform on both sides. What is A? A is 1. Okay, so A is 1. Okay, so the Laplace of y is equal to 1 by s minus e to the minus as upon, now this y0 has been given to us as being equal to 0. So y0 is 0 and this is Laplace of y prime minus y, which is ly minus, this is sly, sorry, there is an s here, sly minus ly. This implies Laplace of y is 1 by s e to the minus as upon s minus 1. Solution has been obtained. Okay, this was a differential equation. It got transformed into an algebraic equation and I obtained the solution, but what is the problem here? I have obtained the solution in the S domain, right? I am not interested in Laplace of y. I am interested in y, right? So I need y which is inverse Laplace of whatever that function is. Okay. I need y which is going to be the Laplace inverse of that function that is there. Okay. All right. Now we have done a lot of algebra. So now let me just go ahead and show you. We just have a couple of minutes, so maybe we'll finish it next time. But now getting the inverse of this guy is not an easy task. Okay. Especially if you have got more terms in here. Okay. So this is where I permit you to use online resources. Okay, I'm okay with that. So let's go ahead and use an online resource and try to see what is it that we are going to be getting. So networks here. So I'm just saying that I have used something called Symbolab. Okay, and over the different classes, I'm going to use different versions of these nice tools that are available. But let us just say that I go here and I type in, I want the inverse Laplace transform. Okay, so I type in inverse Laplace transform and I get a large number of tools that are available. I usually use the first three which Google gives me. So Wolfram Alpha, eMath Help and Symbolab. So these are the ones that I use, but you are welcome to use anything that you are comfortable with. So let me just say Symbolab we are going to be using. Okay, for this particular problem I have said I will use Symbolab. So I have got inverse Laplace there, and in here I had 1 minus s. So I go back here, inverse Laplace I need 1 minus 1 by s, sorry. Okay, so our time is over, so we'll stop here for today, and I'll see you again on Monday. We'll continue here. Thank you very much.